going over some of the concepts you have seen earlier, but in a more, let's say, cartoonish way and from a slightly different angle. So in particular here, we will be focusing on a class of protocols that are called sigma protocols, okay? Those are 3-round protocols where the prover speaks first, the verifier sends a message that we usually call this message a challenge. And this is just a bit string. Okay, think of it just like a bit string or just like a random value. And the prover sends back the reply, okay? We want 3 main properties to hold for this type of protocols. The first one is completeness, which means that when prover and verifier are honest and the prover has the witness and for the statement X that is proving, the verifier will accept. The second one is honest verifier zero knowledge. You have already seen this property. So this property says that there exists a simulator that on input just a statement can produce a transcript, which is indistinguishable from the transcript that is generated in a conversation between a prover and a verifier. Okay, so crucially again, let me stress that this simulated transcript is generated without using the witness. And moreover, let me say this again, this is honest verifier zero knowledge because this indistinguishability here holds, assuming that the prover has interacted with the verifier, which is honest, which means that basically always sends a random challenge, always sends a random second round. There is a variation of this notion, which is called the special honest verifier zero knowledge, where the only difference is that the input to this algorithm is not just a statement, but it's also the second message. So this procedure seems kind of a bit stronger because it says that no matter what second round, what challenge you give me, I will be able to simulate the first and the third round, such that this thing is indistinguishable from the first and the third round that you get from a conversation with a real prover. Okay. So this property here may seem a little bit more strong, but actually you can prove that given any sigma protocol which is honest verifier zero knowledge, okay, so you have a sigma protocol which is honest verifier zero knowledge here, you can transform this in a new sigma protocol which is special honest verifier zero knowledge instead, okay? So just this is a very simple exercise, and just think about how you would do this maybe over lunch, and then come and talk to me. Okay? It's a very simple mental exercise to do. There are also like variations. So I will mention this in the talk a few times. So all the definitions that I will mention, some of them have like the computational version, which means that things are indistinguishable as long as like your adversary is a probabilistic polynomial time, or things are statistically indistinguishable, which means that you allow the adversary to be unbounded. Okay? That's the difference between statistical and computation. That's the only thing you need to remember. And then here I'm introducing a notion of a different notion of soundness, which is called special soundness. And special soundness guarantees the following. It's very similar to the concepts you have seen earlier, but it is defined in this way. So if you have 2 transcripts, okay, you interact with a prover and the prover gives you, somehow you manage to receive 2 accepting transcripts that share the same first round. Okay. The second round instead is different. The challenge is different. So if you are in such a situation, you can always extract a witness for the statement X that has been proven. Okay. Okay. So let me recall again, like, what is the notion of proof of knowledge, because we will use this notion a lot. So this notion basically says that if you have a corrupted prover that convinces you with some good enough probability, this means that you have an extractor that can extract the witness, okay? Can extract the knowledge of this prover. The way extraction is performed is again by giving to the extractor this what we call black box access to the prover. Okay, so think about like if you have an adversary that does something, it means that this adversary can has a code. So you give the code to the extractor, and actually the extractor and all the simulators that we will see in our definitions cannot access to the code, but can only query the adversary as it was like a black box. Okay, so what the extractor can do here is to feed this code with some randomness and interact with it. Okay. When I say that we rewind the adversary, what I mean is just that, I mean, this is a code, so you can restart a code, you can run the same code multiple times. Rewinding means that you just take the same randomness or a different randomness maybe, and you restart the adversary. So restarting the adversary allows you to interact with the adversary a second time and maybe change something in your interaction. So what you can prove is that if you have a Sigma protocol that is special sound, then this Sigma protocol is also proof of knowledge. And the reason is that what the extractor can do is that it can proceed in an execution as it was like an honest verifier against the prover. And then because we can restart the prover, we can restart the prover and send a different message here. Okay. And if we get a reply, here we can just apply the special soundness property because we have a fixed first round. We have two accepting transcripts for different challenges, so we can extract the witness. Okay? So just a little intuition about why this holds. Things are a little bit more complicated because you need to remember that it's not like you rewind the adversary and the adversary replies you. No, that's written nowhere. Okay. The problem is that adversaries can do whatever they want. In particular, they can abort. So if you rewind this guy, it doesn't mean that he will reply to you. You may need to reply the adversary multiple times. And that's why you need to be careful because these type of extractors are not necessarily polynomial time, but they are expected polynomial. Okay, this is a technicality, but it's good that you remember this thing. Okay, let me give you a few simple examples. The most typical and simple example is the Schnorr protocol, where you have the prover that wants to convince the verifier about the knowledge, about the fact that he knows the discrete logarithm of x. Okay. So how can we do that? So the protocol proceeds in this way. The prover takes a random element r and computes g to the r. So the verifier replies with the random challenge, and then the prover replies it with the third round constructed in the following way. Okay, it's r, the randomness you use to compute a plus the challenge times your witness. Okay, the witness here is the exponent, and the verifier accepts if g to the z is equal to this thing over here. Now, if you look at it, you will notice that like completeness holds because if both parties are honest, then g to the z is equal to g to the r plus cy, and this is exactly what you have on the right hand side. There is nothing particularly special happening here. So to prove that this is a Sigma protocol, you need to prove then that you have these other two properties. Special soundness is the other one. Again, so if you have two accepting transcripts, two different challenges, like we need to prove that we can extract the discrete logarithm. So now, if you look at z, okay, so z is equal to r plus cy, right, here. Z prime is equal to r, it's the same r, right, because they share the same first round, plus c prime times y. This is c prime and this is y. Now, if you look at this thing, you can actually solve it because like, you know, z prime, z, you know, c prime, you don't know r and y. Okay. So it's a system of two equations where you don't know two things and we are very good at solving these things. And you can extract the witness. Okay. This is an example of how you can do this. So zero knowledge against honest verifiers. Again, because we are assuming that the verifier is honest, it means that the second round here will always be a random value. Okay. So when we need to simulate a transcript, it's very easy to simulate the second round because it's just a random value. So run your simulator, the first thing you do is that you sample this random value. And now, remember, we don't have the witness. How do we generate A and Z such that they are indistinguishable? Well, if I know C in advance, and that's the usual trick that you will see in many examples, is that if you know C in advance, you can just generate A and Z in a very simple way. Okay, so this is what Jonathan was saying earlier, is that zero knowledge does not contradict soundness, and the reason is that soundness comes from the fact that the prover here sends a message, and then he needs to wait. He doesn't know this challenge message when he's generating the first round. Okay? The simulator here has a big advantage because the simulator can choose all the things. In particular, the simulator can pick the second round before generating anything, and then he can produce everything accordingly to this second round. So the life is much simpler for the simulator. Yeah. And that's how you output your messages. Okay, so let me give you another example. So that one was a relatively trivial protocol, also because like you are there is really nothing to prove sometimes about the knowledge, like about a group element, because like in many cases you know that that's kind of a group element that has a discrete logarithm, so you're mostly interested in proving like the knowledge of the discrete log. This is just another example where like what we want to do is that we want to prove that a given tuple is diffie. This is useful in many applications. Diffie-element tuples are like very useful. Just as a reminder, so a tuple is diffie-element if it has this structure here. So you can think about it as a tuple where you have a base G and a base H, and you have two elements U and V, and you want that the discrete logarithm of these two elements kind of is the same. That's what you want to. So why is it interesting to have a proof or a zero knowledge proof for this type of tuples? Is because like we think that it's difficult in general to distinguish a tuple that is diffie-element from a tuple that is non-diffie-element. Okay, so then as you can imagine, it becomes useful. Like if I have a way to convince you that the tuple is diffie-element in a zero knowledge way, like can be a nice thing to have. Okay, and so this is what I mean. Like when it's difficult to distinguish diffie-element tuple, means that you know with probability 1/2 I pick a tuple that is diffie-element. So here these two guys have the same exponents, and here they don't have the same exponent, and the probability that adversary guesses the bit be correct is 1/2. Okay. That's what it means. So to prove that the tuple is diffie-element, you can actually slightly modify the protocol I showed you before, because the protocol I showed you before is like to prove the knowledge of a discrete logarithm. Here I need to prove you that two elements have the same discrete logarithm. Okay. So what I can do then is the following. Remember that the kind of the base of one of the value u like was G and the base of V was H. Okay, here. So what I can do is kind of like almost like running these two sigma protocols in parallel. Okay. Where I just compute the first round accordingly to H, and then the rest of the sigma protocol remains the same. So this should give an intuition of like, in particular, like if you think about what this problem is, which is again like proving that the two elements have the same discrete logarithm, you should get an intuition that this kind of should work. Okay? I won't go over this because like it's very similar to what I've seen before, and let's go to the more interesting parts. So now, why do we like sigma protocols? We like them because they have some interesting properties. One of them is that you can efficiently compose sigma protocols to create more like interesting languages. So for example, let's say that I have now two instances, x0 and x1, and I want to prove you that only one of them is a true instance. Or for example, think about x1 and x2 as two group elements. I want to prove you that I know the discrete logarithm of one of these instances. Okay, so what can I do? So you can do the following. So first of all, just a reminder, those are Sigma protocols. So the black protocol and the purple protocol, they both are equipped with these simulators. So let's say that you have a prover that just knows the witness for x0, for the statement x0. So given that the prover knows the statement for the for x0, we can just run the standard prover procedure using the witness .0. And for x1, the prover doesn't know anything. So the only thing we can do, we can try to run the simulator, and that's what we output. Okay, we run the first round of the black Sigma protocol and the first round of the purple Sigma protocol, where only one message is kind of generated using the witness. So the verifier now sends a random message. And now the tricky point here is that we have no hope to kind of answer correctly to like both this message and this message to create like a valid answer to both these first rounds. But what we can do is the following. So we compute the challenge C0 as the XOR of C and C1, which is like the challenge, the message we have obtained by simulating the purple transcript. Okay. So we get a new value C0. This is a random challenge. So C is random, so this C0 will be random. And the point is that we know the witness for the Sigma protocol Sigma 0, so we will be able to generate a valid answer. C1, we have chosen it at the beginning, so we can just send the simulated transcript, and this kind of ends the protocol. Okay. So the reason why we are doing this mess here is because ultimately you want to hide which of the two witnesses the prover. Okay. So, and moreover, what you can prove is that this thing that we have just designed is still a Sigma protocol. Okay. So, any questions here?
Does this work in general, like with the XOR?
This works in general, yeah. So if I think one simple way, you just think about this thing as you can always kind of parse things as bit strings, okay? Just parse it as a bit string, you do the XOR, and you get this, and this holds again for every Sigma protocol. It doesn't matter what the protocol does, this holds regardless. Yes.
Does it generalize somehow to the non-binary challenge case? Like, you can just sum the challenges?
Sure. If you don't want to do the conversion and you have challenges that belong to the same domain, you maybe can do something smarter like addition or subtraction, but you need to be careful, of course. Okay. Yeah. But if you really, these things are very different from each other, just of course you need to do some padding. In practice things are always not as simple as you see on
the same concept. You can simulate n-1 branches and you do one branch and then you do something with the challenge.
Yeah, so you can extend this idea to the T out of n case actually, where instead of doing a 2 out of 2 secret sharing here, you do a T out of n secret sharing. I will not give you the details of this. Like, think about it. It's not complicated.
So, but what holds is now either the transcript will fail if it didn't, like, for both verifications. So the verifier will verify C0 Z0 and C1 Z.
Yeah, exactly. So the verifier will, let me see if I have it. The verifier will accept only if both these conversations are accepting, and if the challenge C is equivalent to the XOR of C0 and C1. So okay. Now we want to prove that this is still a Sigma protocol, because if you can prove that, this is nice, because like then we can maybe use the Sigma protocol as input of another or composition, and we can create like more sophisticated proofs for like more sophisticated languages. Okay. The first thing I want to prove is special sound. So again, first round is fixed, but I have two challenges and I have two accepting transcripts for this big protocol. Okay. Now, if I have like one accepting transcript, it means that the verifier accepted, and this means that these conditions are verified. This is what I showed you in the slide before. But I also know that this thing here is accepting, okay? So this means that also this is like, these conditions are satisfied. Okay. Now, what I know is that C is different from C prime. And this implies that either this is different from this or this is different from this. This is just from property of it, so. But I mean, if at least one of them is different from the other, this means that by the special soundness, I should be able to extract the witness, at least from one of these conversations, either the purple or the black, okay? For example, if C is different from C prime, and this is because like C0 is different from C0 prime, then I can extract the witness W0 and I'm happy, okay? I'm happy because this is a witness for the entire protocol, because again, what was I proving? I was just proving to you that one of these two instances is valid. So I need only one witness, either W0, W1. This is valid witness, and so I'm happy. Okay, so now we know how to do this OR composition. Let's say we want to do the AND. Okay, I want to prove you that both x0 and x1 are true statements, or that I want to prove you that I know the discrete logarithm of both instances. Okay? So this is a question for you. Like, do you have any idea on how to do it? Actually, a more maybe a structured question is like, maybe one thing I can do is the following. So I run the sigma protocol for x0, and in parallel, I run the sigma protocol for x1. So I do this in parallel. So my question for you is that, does it work? So more precisely, am I constructing a sigma protocol for this AND language? So would think the answer is yes. Would think the answer is no. Okay. Why is it no?
I would learn if it's like in x0 and not in x1. Or
Say it again.
if I mean, if it's rejecting, then I would still know something about it. No, I would know.
So the honest prover, let me clarify. The honest prover would generate this transcript using the witness, because remember, we want to prove that I know the witness for both x0 and x1. So I will generate this is generated using the prover procedure of this protocol, and this is generated using using the prover procedure of this protocol. Okay? Yes.
I think we got a problem because now we need to get both witnesses when we're extracting, and it's possible that one of those challenges is the same, but they don't need to be mutually different.
Exactly, that's exactly the problem. Okay, so the honest verified zero knowledge property works fine. The problem is in the extraction. So because special soundness says that as long as the challenge is different, I should be able to extract. So this means that if the challenge differs in 1 bit, I should be able to extract. But if a challenge differs in 1 bit, maybe it differs only, with respect to this challenge here. So I will never be able to extract the witness for like x0. Okay, or that's what happens. So the next question will be, how do I fix this? There is a simple way to fix it. You? Yeah?
You use the same challenge.
Just use the same. Yes. Just use value C. And that's exactly what we do. Okay.
But is there actually like a attack on the protocol if we don't do that? Or
Is there
it's just a formalism thing?
No, it's not a formalism. If I don't do this, then when I try to prove that the protocol is special sound, I will fail, or at least I don't.
The question is this just a formalism to be able to prove it here, or is there really like a problem in the construction that I can say, okay, if you're doing this, then I know you can extract some knowledge about.
Oh no. So it's not that. It's just that you're creating a protocol that has a weaker security in terms of soundness. Okay. So I'm providing you something that satisfies something that I have defined that we like for some reason. I mean, we like because, for example, that implies proof of knowledge, which is a great property. And if you start doing this thing,
I'm just wondering, like, if this means that it's not the original definition wasn't general enough, because it seems everything would work even if we allow for two different challenges here, and it's just that our initial definition maybe was too constrained somehow.
That's a good comment. Indeed, there are relaxations of this definition, and for example, you can define a notion of the special soundness where you require not 2 accepting transcripts but more of them. The thing is that some of the nice claims we have about sigma protocols then don't necessarily hold if you relax the notion of special soundness. This becomes very problematic when you use the Sigma protocol in more complex protocols. For example, when you try to, we will see that later, but when you apply FHMIR or when you do other things, let's say, sometimes it's very, very comfortable to have this special soundness property. Sometimes you cannot get it, and it's fine. Could be fine for your application. You just need to be more careful in your security proof. Just to say, many mistakes have been done, like because of this, like because you take a protocol that is not special sound and you just use it as it was special sound, and very recent mistakes actually. Okay.
I mean, I think you can prove that it's still a proof of knowledge, but
Yes.
not special sound.
I agree. Yeah. Okay. So we have discussed. Okay. I just wanna mention this like Qt application, like you can do like using Sigma protocols, and then we'll go to the more spicy stuff. So Jonathan already described you what commitments are. And what I'm gonna tell you now is that you can design some special type of commitments just using Sigma protocols. So in particular, we will design commitments that are instance dependent. So what I mean by that is that when you commit, the input of your committing algorithm will be your instance, an NP instance, and the message, okay? And the output is just a commitment and the commitment information. To the commit, you just have the commitment algorithm that returns 0 or 1 to kind of tell you whether like the commitment information is correct accordingly to the committing information. So what we want is that when X is in the language, then this commitment is hiding. Instead, when X is not in the language, we want that this commitment is binding. Yes.
Isn't the first step of a Sigma protocol itself a committing step?
Correct. So
you already need access to some commitment primitive in order to.
not necessarily. The way I define Sigma protocols, like I never mentioned commitment there. Kind of, there is nothing in the definition. To be precise, there is nothing, at least, that clearly states that there must be a commitment of something somewhere. But what you're saying is true, and indeed, you will see now that to construct such a scheme, we do something that you would expect, in the sense that to commit, what we can do is that we can commit using the special honest verified zero knowledge simulator, using as input the statement X, and instead of using the challenge here, like we will kind of parse the message as it was the challenge, as it was the second round of the problem. Okay? And our commitment is defined by A. So A is the first round of the Sigma problem. Yes.
Sorry, once again, where is the challenge in the green box?
So the challenge is the message. Instead of like, I'm treating the challenge as the message.
It's only for binary messages in this case.
It's for, I mean, again, this simulator works for whatever type of challenges your Sigma protocol.
Okay, so but it's
So I'm assuming that the message is in the space of the challenges. And like to the commit, like you just return everything, like also the third round of the Sigma protocol, and you just run the verifier of the Sigma protocol to check that everything is fine. Okay. So now I want to prove binding. Okay? I will prove binding and hiding. So one question, so binding, what we want to prove is that when X is not in the language, then it must be that this commitment is binding. Binding means that there is no way that you can find two different messages that make the verifier accept the same commitment, bold commitment, okay? So now a question here is like, what property of the Sigma protocol am I using here, or should I use here to prove binding? Because the Sigma protocol has like two kind of main properties, which is honest verified zero knowledge and special soundness. So for the binding, what property do you think? Yeah.
Special soundness.
Special soundness. Because the idea is that, I mean, it's quite obvious that if I have a commitment that is accepting with respect to two different messages. This means that I have a conversation for a message M and a conversation for a message M prime, and those are challenges, right? So if the challenges are different, it means that by the special soundness I can extract the weakness, but this means that then X is in the language, and this is a contradiction.
Sorry, Michele.
Yes.
Why did you define the binding property only with respect to messages? Sorry, with respect to X is not in the language. Is that a
Because if X is in the language, how do you prove that?
I think this was the prerequisite. We wanted to construct a Sigma protocol that has exactly this property.
So we wanted to
Binding
construct a-
is not in the language.
We want to construct a commitment that has this exactly this property.
This
That when
X
X is not in the L, you have binding. When X is not in the language, you have binding.
Okay.
If X is in the language, binding is not guaranteed.
yes? Okay.
Okay, that's what I'm saying.
How is this? Okay, and how is hiding relevant to the X in language or not?
So when instead we want to do hiding, okay, X is in the language, right? Why do I need that? So because the security proof works in this way. So what does it mean that the scheme is hiding? It means that you have an adversary, gives you two messages M0 and M1, and you like commit to one of these two messages, okay, at random. And you want that the adversary doesn't understand what you have committed to. So we are in this security game, we send this commitment to the adversary, and the adversary says, okay, you have committed to the message MB prime. Let's assume by contradiction that the B prime is equal to B. B is the message, I'm committed to MB. Okay, so the adversary here is very smart, he understands what I've committed to. Okay, so now let's see, this is what we have done. We have to commit, we have run the special honest verifier zero knowledge simulator, and we have generated these two things. And our commitment is just this. Okay. Now, what we know is that by definition, okay, this entire transcript actually is computational or statistically indistinguishable depending on the Sigma protocol, what transcript generated using the witness. Okay. So this is the part where I'm crucially using the text belongs to the language. But this holds true, and this also holds true. Like in particular, note that this is indistinguishable from this message, and this message contains zero information about the message. Okay, so this means that this thing cannot leak anything about the message. In particular, what I can argue is that this is also indistinguishable from this, where this is the output of a simulator which is executed on the message M1. It's like a sequence of hybrids, okay? This is an intermediate hybrid, where I start from the experiment where I commit to the message M0 and end up in the experiment where I commit to the message M1. Okay? And this sequence the first hope holds because of the honest verified knowledge simulation, and the same holds for the plus.
It's kind of the prover cannot make use of the challenge. That's the message.
Exactly, yeah, it's crucial that the prover, by definition, the prover doesn't know the challenge. So this thing is indistinguishable from something that doesn't use the message, doesn't use the challenge. Okay? And this is kind of the core idea of everything that we define secure, which is I can simulate something that contains maybe an information about the message, and I can simulate this thing with a procedure that doesn't take the message. It's always the same idea. Exactly. Okay, and this is this is a tool that may seem strange, but this is very useful in many applications, in particular when you are designing more sophisticated protocols, and it becomes quite useful to have this type of commitment schemes. Okay, so far what you have seen is that we have seen some Sigma protocols for very specific NP languages. Yes.
We can ask a small question on the commitments.
Yeah.
And I saw another hand. So in practice, we can use it because the verifier doesn't really know if X in the language or not. Yeah, this is a weird commitment because it has one property if X is in the language and another property if it's not. So it's never two at the same time. But because the verifier doesn't know, we don't care. How does it work?
So
We use it as a regular commitment.
So the point is that if the verifier does know, for example, that that statement is not in the language,
Yeah.
and like or like whomever knows that the statement is most likely not in the language, then and I care about binding, because there are situations where I only care about one property.
Okay.
You know, usually a party in some cases either cares about binding or cares about let's say about secrecy, right?
Right, so you can kind of design your scheme so that the commitment scheme is like one case,
Yeah.
has one property in one case, not another case.
Either I'm the person issuing the commitment and I care about secrecy, but I don't care about binding. Or I'm the person receiving the commitment and I do care about binding a lot, but I don't care that the commitment is not hiding. So it really depends on the application, and in particular, you know, this is kind of very useful when you do, like when you use it in like to design more sophisticated protocols, in particular zero knowledge protocols. Okay, so so far we have seen that. So by the way, many interesting languages have Sigma protocols, and as you have seen, like those are very efficient. Like it's just few exponentiations to prove that to prove the knowledge of a discrete logarithm, for example. The problem is that there are just honest verifier zero knowledge. Okay, so zero knowledge holds against the verifier that's assumed to be honest, and the other, so this is something we don't like. And the other thing is that, okay, but can we have Sigma protocols for NP? And how do we get security for malicious verifier? Okay, those are the two main questions we wanna answer now. And okay, so one question Jonathan Descander already answered. So I will not recall what commitments are because I've already mentioned it, and Jonathan has also mentioned it. But I'll just tell you that you know, commitments are not necessarily just interactive in the sense that the commitment phase may involve multiple interactions with the verifier. Okay, so the type of commitments we will consider here may have an interactive commitment procedure. They may have an interactive decommitment procedure. Okay, and just remember that you know, we may be interested in hiding the message in a computational sense or in a statistical sense, and the same holds for binding. Okay? One thing to recall is that I mean, if you don't know that, think about it, then you should be able to come up with a proof is that you can never have a commitment that is at the same time statistically hiding it. Just remember this. Okay, so those are just examples of statistically binding commitments. This is like using a modification of Algamal encryption. I don't think I will go over them. And this is like commitment that you can be designed from pseudorandom generators. Okay, I have this picture mostly to tell you that you know, you can do commitments from a very simple primitive like pseudorandom generators, which means that you can do commitments from one-way functions. Okay, I will not do this, but you can do these from one-way functions. Only one thing you need to be careful is that in this case, in this scheme, the commitment procedure, the commitment phase is indeed interactive. Okay, we don't know how to do. I think it's maybe even impossible. This I don't know whether it's possible to do this like non-interactive from just one-way functions. Okay, and just why I stress one-way functions, because one-way functions are it's kind of like one of the most basic primitive we have, and in general, like it's nice if we can do and design one-way function. And I'll mention this. Okay, so what is the Sigma protocol that we can use for all NP languages? And here we have our friend again. Okay, so I'll go relatively fast over this, but let me recap it again. So what we will design is a Sigma protocol for Hamiltonicity. Okay, so to prove that the graph is Hamiltonian. Okay, and this is basically the protocol that Jonathan showed you before. I'm just gonna prove you that this is also, like, in particular, a Sigma protocol, and we can do a lot of interesting stuff with this very simple Sigma protocol. I mean, it's not that simple, but anyway. So just to recap, so we have a graph and we have the adjacency matrix of this graph. And okay, where there is a 1 anytime that two nodes are connected. Okay, and so this graph, for example, has a very simple Hamiltonian path. And so what we the reason why this is relevant is that we will focus on designing a protocol which has some very interesting property, okay, P, for the language of Hamiltonian graphs, and then we can argue that, you know, actually every language in NP has the same properties. Okay, that's why we really like Hamiltonicity. So as you saw before, one thing we will use to design this protocol is the fact that I can always kind of start from a graph and have the same graph, just with a different labeling of the nodes. Okay, this is what it means when I do a permutation. I just, for example, in this case, the first node was 0. I pick a random number. Okay, 3. Good. In this case, this node was 3. Okay, 0. Okay, that's what it means that to do a random permutation. Okay? And this is the matrix you get. Okay? Pi is the permutation, which is like the table that tells you which vertex correspond to the other vertex. Okay. Now, of course, the simple question is like, if this graph has an Hamiltonian path and an Hamiltonian cycle, does this graph have an Hamiltonian cycle? I think yes. Yes, obvious. Okay, good. Fantastic. Good. So let me recall the Sigma protocol that Jonathan showed you before. So the first thing the prover does is that it takes a permutation. Okay. So the statement we want to prove, remember, is that G is Hamiltonian. So we take a permutation. We create the matrix that represents this new graph H, and we commit one by one to all the entries of this matrix. Then the verifier has two choices. Okay, he can either ask us to open everything. Okay, so when the challenge bit is 0, we open to everything, and we show like, look, this is a permutation. This is actually just like the graph G. Okay, and the verifier checks that this is true, and this is kind of an efficient process to do. When instead we have 1, we open just to a cycle. And then the verifier just checks that this is indeed a cycle, and if it's true, then the verifier accepts. Okay, I don't want to go over this again. Okay, now we want to prove that this is a Sigma protocol. So again, special soundness and honest verified zero knowledge. Special soundness. So we have this situation here. The first round is the same, and I have a reply for 0 and a reply for 1. How do I extract the cycle for G from here? Well, this is relatively easy, right? Okay, so first of all, what is the cycle I have here? I mean, here I have a 1, right? So it means that the cycle is a path from 0 to 3. Okay, from 3 to 1, and I write 1. Then I have something from 1 to 4, and I write it there. Okay? So this gives me basically a cycle in H. Okay? But what I want is a cycle in G. But that's very easy to do because I can just use this translation, this permutation, to go from this cycle in H to a cycle in G. Okay? So 0 corresponds to 3, 3 corresponds to 0, 1 corresponds to 1, and so on. Okay, and you get the cycle for G. Okay? As you can see, this cycle here is exactly the cycle I have here. Okay? This is the same, right? Okay, good. So note that here, so this proof is kind of like sketchy because the way you prove it is via a reduction to the binding of the commitment. Okay? Indeed, note that this holds true only if there is no way that the adversary can open the commitment to do different values. Otherwise, here, instead of having like 1, I could have a 0. Like, you know, I could like open to a completely different graph. So this holds absolutely because the commitment is binding. Okay? We can prove that, you know, if the prover does something messy, we can construct a reduction. I will not show you the reduction, but kind of be aware of this. Okay?
It's not the same cycle, it's the opposite direction kind of the cycle. The cycles are not the same.
It doesn't matter.
The direction is different, right? Yeah, but it's not a cycle.
I mean, no, but this is like not directed, for example, right? It's fine as well. So it's the same.
It doesn't need to be the same either way.
Yeah, it doesn't need to be the same one. That's, yeah.
Okay, just to verify, we're trying to prove that I know of a graph that has a Hamiltonian cycle. Is that the statement?
So the statement said here, this graph has an Hamiltonian cycle. That's So the language is like, I want to prove that an instance belongs to the language, and the language contains all the graphs that have an Hamiltonian cycle. Good. So now I'm just proving to you that this thing here is a sigma protocol, which means you have special soundness and honest verified zero knowledge. Okay. And in particular, you know, this like should tell you that you have some form of soundness here, because like, you know, just by the fact that I can do this extraction, this should tell you that, okay, there is some truth in this statement, okay? So we will modify this protocol very soon to guarantee that you have also like good soundness. Again, like the way, you know, what Jonathan said is that if you just want to run this protocol and you want to use it to prove to someone that the graph is Hamiltonian, here again, the cheating prover can cheat with probability 1/2, okay? Because I can just get the bit, I can just guess the bit, I guess the bit, and then I commit, you know, appropriately. Okay? What I mean, yes.
Assume in the real world, this would make sense only if the graph was really big, because this is so small that eventually you can piece things together and.
Yeah, I mean, like this make, you know, the point is that if the graph is small, you can compute the solution maybe on your own, and so that's trivially kind of everything. Okay, the simulator would just return the witness, and you know, the protocol does nothing, right? So everything here makes sense only if we believe that we have an interest in protecting something, because that something is valuable, because not everyone can have it. Not every polynomial time algorithm can generate it. Okay. Like, yeah. Okay. So honest verified zero knowledge. How do we prove it? So if I know what is the challenge, remember the honest verified zero knowledge simulator knows the challenge. So if I know that the guy will ask me one, when I get asked one, I just need to open a cycle, and yeah, I just commit to a matrix of all ones, or I'm always capable of opening to a cycle. Okay? Instead, when I know that I will get asked 0, I need to open to a permutation. I can compute the permutation. I don't need the witness. I don't need anything. I can just open to a permutation and open to it. Okay? So this is how you simulate. Knowing the bit here, you can simulate. Okay? Are there any questions here? This is like kind of a recap in some sense of what Jonathan said before. Is this thing here? Okay, good. So let's move on. Now, we said that we don't like this protocol because it's secure only against the honest verifier, right? We don't want that. We want this protocol to be secure against an adversary that does whatever it wants. Okay. In particular, we want that you know, these two things are indistinguishable. Okay. This is like the experiment where the prover uses the witness to convince the verifier. Okay, about the validity of the statement, and this is like a simulated experiment where I can return whatever this guy can return, but without using the witness. Okay. If I can do that, like this means that my protocol here doesn't leak anything about the witness, because trivially I can kind of like generate something that is indistinguishable and doesn't use the witness again. Just as a recap. And in particular, the notion of zero knowledge we will consider here, it's called the black box zero knowledge, and the same way as proof of knowledge, because this simulator here has, again, black box access to the corrupted verifier. Okay? Just remember one thing, when I'm talking about zero knowledge, it's always the verifier that is corrupt, because that's the guy that is receiving the proof. When I talk about soundness, it's the prover that becomes like the P star, because it's the guy that wants to convince you about something that is not necessarily true. Okay. Okay. So how do we achieve zero knowledge? And actually, what you can argue is that when you the protocol I showed you before, like actually every Sigma protocol, okay, where the challenge is 1 bit, is also zero knowledge. Okay? And how does the simulation work? So remember, this guy now, the verifier, is corrupted, so he can do whatever he wants. He can even always ask for the same challenge 0 all the time. It's not random. So what the simulator can do is to sample a random bit and generate a transcript ACZ, send the first round to the adversarial verifier, and now we hope that we get a B star which is equal to B. Okay. If that's the case, we are done with the simulation. If it's not the case, then we restart the adversary. We run the simulator again. Okay. And at some point, the adversary will will reply with a bit array which is equal to b, and then we can conclude the simulation. Okay. So with an expected number of rewinds, if I do 2 rewinds, expected, because the guy can abort, I will be able to simulate, and yes.
I have a question about how much we control the randomness of the adversary here.
Yeah.
We don't, right? Because otherwise we
So the adversary takes a randomness, right? But the adversary can ignore it. Of course, the question would be like, okay, well, why would the adversary change his answer here? Maybe. And the adversary changes his answer here because the adversary is receiving a new first round every time. So you may have an adversary that, of course, if the adversary replies always to the same message, regardless of the first round, that's great. I will guess it with probability 1/2. If he doesn't, it means that he's doing something. For example, this output here is the output of a pseudo-random function evaluated on the first round. But again, anytime I rewind, I complete a completely new simulated proof here, which means that the output of the pseudo-random function will be kind of, let's say, random. That's not true, but it will be random is not the right word, but it will be something else.
So we are allowing different randomness for the prover here in the rewinding?
So you are rewinding the verifier, okay? Zero knowledge is for protecting against a corrupted verifier. So that's the guy that we have the code of this guy in a box, and we can restart. So we are allowed to rewind the verifier, and that's how we do the simulation, okay? And of course, this guy is malicious. So we give a new randomness. The guy can just ignore it because maybe he has an internal randomness and always uses that one. You can ignore it. But the point is that if that's the case, anyway, when you rewind it, will just behave as before unless you change something. Okay?
But we are allowing the verifier to accept that randomness or not.
The verifier is malicious, so the verifier is like this is an algorithm that takes some randomness and may use it or may not. We don't know what it does. We really have no idea. We just know that it's deterministic once you fix the randomness. That's important. If it's not, then nothing of what I'm saying here works. But this is a discussion for maybe the end of the talk.
But this somehow implies that the A cannot depend on the B in the output from the SHBZK algorithm, no? Because otherwise, malicious verifier could somehow try to extract information from the B from the A, and then he would always reply with the same B. It's the same B that I chose in the beginning. B star would always be.
So right. So the point is that if something like that happens, it means that this guy here can somehow see what is encoded in A. But this would contradict the fact that this protocol is honest verified zero knowledge, because we said that the first round here actually doesn't contain information about the message. Okay, so that cannot be. Of course, I'm simplifying things, but that's how you would need absolutely this argument. Yeah. All good. Does it make sense? Yeah.
Could you repeat what happens if B is never equal to B star?
It's fine because no, that cannot happen because like there are two cases. Either this guy here has always the same B, for example, and then I will pick this bit with 0 or 1 with probability 1/2.
After performing some interactions, we see that he always responds.
You don't even need to look at what it does. The point is that because this thing is honest verified zero knowledge, that this B star cannot depend on this B. That cannot be because this thing is honest verified zero knowledge. Okay, so good. So are we happy with this protocol? No, because
To ask, like, so far we have this thing, but for soundness we used amplification before to get a meaningful soundness, and so far you haven't mentioned.
Yeah.
Yes, if we have a channel space, it's just 2 bits. Yeah.
Yeah, I haven't mentioned it, and indeed,
On the size of the channel.
yeah, exactly. So the way you have seen, before to amplify soundness, it works fine, perfectly. What we may not necessarily like about that approach is that the number of rounds increases a lot, like increases security parameter. Okay. So what we want to do here is actually to show you, I want to show you a way to not have this blow up. Okay, in particular, I will show you like the best possible protocol you can have, the best possible zero knowledge protocol you can have in terms of round complexity. And this like will be the main tool. In particular, I'm going to use this tool now to do something interesting. So this is what we said. And this is what we ultimately wanted to do, okay? Toward the end, we will have a constant round protocol. We will see what is this constant, but it will be the best possible constant you can have. Moreover, the soundness like will be good. Soundness error means the probability that the adversary convince you, that a malicious prover convince you, it's small, it will be negligible. And all this stuff, all this protocol will be based on the best possible assumptions, okay? Which is one-way functions, in my opinion. So one-way functions are good. Okay, so then Jonathan left you with one question, like, can we just take the protocol, instead of repeat it in sequence, we repeat it in parallel? Okay. So my question here is like, you know, does the simulation approach we had before work? Okay, the approach before was like, I send the first round, I rewind, and you know, I hope that the challenge is the challenge I like. Okay. So does it work?
It was like a lot of rewinding.
A lot of rewinding, right?
Exponential error.
Yeah, that's kind of a lot of rewinding, right? It's like expected decay. Okay, so that doesn't work. You can actually, I will actually argue what happens when you try to compose protocols in parallel in concurrency. You will see that later on. So in general, things don't compose well. Yes.
Is the assumption that like the verifier will never reach the end of one before the other?
No, the thing is that the verifier, you know, will kind of send you the challenge, okay? But remember, how was the simulation approach working before? We were like, let's take a random challenge. Let's take a random bits. In this case, like the challenge is like k bits. I take a random k bit long string, and I perform the simulation assuming that that's the challenge I will get. And then I hope that I get that challenge, okay? Now, if I do this process in a randomized way, and again, like, you know, this guy is also randomized in the sense that the guy sends you a random challenge. So this means that the probability that you guess correctly is 2 to the minus k. And that doesn't work. Okay. Okay, so that's the problem. We cannot, you know, simulation doesn't work. And I will show you actually that there is no way you can make a proof here. This thing just cannot work. It's not because we are not able to prove it. It just doesn't. Okay. But what is nice is that this tool can, we can use this thing to if we relax a little bit the security notion, instead of requiring zero knowledge, we require something less. Actually, this approach works and gives us an argument of knowledge. So a proof that is actually good, that has a small soundness error. Okay. And this will be the witness indistinguishability. So maybe I should stop here, and so we have lunch and we're all happy, and we come back here.